Hello everyone, I'm J Wildberger. So today I want to wrap up this discussion of how we construct the true complex numbers in a much more general, algebraic, and sort of enlightened way of proceeding that actually connects with all kinds of other interesting things, including relativistic aspects of complex numbers. Okay, so our idea is that really behind the scenes there is this algebra of dihedrons, and that really controls the story. And we're talking about working over a general field first of all, so it's very general. F is a field, and then we consider the dihedrons 2x2 matrices with elements in the field. This is the algebra of dihedrons. And crucially, this thing has a conjugation. Okay? This is the fundamental kind of building block that this algebra has. The star of A, B, C, D is the adjugate D, B bar, C bar, A, where of course B bar is the same as negative B. And a crucial property of the conjugation is that R and R star commute. So R times R star is the same as R star times R for any dihedron R. Okay, so then this conjugation has some key properties. It's linear. It's linear both with respect to addition and with respect to scalar multiplication. And crucially, it has this adjoint property that the star of R1, R2 is R2 star times R1 star. So this makes the dihedrons a star algebra with identity being the usual identity matrix. So this is a very nice starting point. So if you had to explain, what's going on to somebody, this is a good starting point, that we're starting with the dihedron algebra, which has this crucial conjugation, basically the classical adjoint or adjugate, that has these very nice properties. That is the setting in which complex numbers are built up. Now the conjugation has one extra really important property that we need to single out and understand. We'll call this the conjugation property. So for D a dihedron, D star equals D precisely when D is a multiple of the identity. In other words, that it's a diagonal matrix with constant elements down the diagonal. So this is a characterization of those dihedrons which are preserved under the conjugation. And it's an easy property to check. You just check it against the definition of the star operation. So this has a number of interesting consequences that just follow from the conjugation property. That if you look at D plus D star, for D an arbitrary dihedron, that this thing here will be invariant under the conjugation. And so necessarily it has to be a multiple of the identity. And so we'll write that multiple as 2 times T of D. And then that brings into being this half trace. T of D is then the half trace of D. So that's a way of sort of getting at the half trace from the conjugation. And if we look at something else which is invariant under conjugation, the product of D and D star, that will also be invariant under conjugation. So by the property up here, it also has to be a multiple of the identity. And if we define that multiple to be Q of D, then that defines the quadrants of D, which you all know is just the determinant of the 2x2 matrix. So exactly in coordinates, T of A, B, C, D is A plus D over 2. It's the half of the trace. And Q of A, B, C, D is the classical determinant, AD minus BC. And then we have some pleasant properties of the half trace. It's linear, okay, and pleasant properties of the quadrants. It's multiplicative. Quadrants of D1, D2 is quadrants of D1 times quadrants of D2, crucial property. And it's also quadratic in the sense that if you multiply D by lambda, the lambda pulls out as a lambda squared. So it really is a quadratic expression. And I've emphasized to you the importance of the fact that this is actually a quadratic form in this situation, making it very, very special and unique in mathematics. So the idea here is that a lot of things that you're used to being associated with complex numbers are actually specializations of things which are happening in this broader, bigger context of dihedrons. And that typically understanding this clarifies what's really going on. So another example of that is what we might call the scalar and vector parts of a dihedron. Okay? So if D is a dihedron, then we can consider these two combinations, D plus D star over 2 and D minus D star over 2. And algebraically, you can see that the sum of these two things is just D. This is a way of decomposing a general dihedron D into two sort of special kinds of things. So this is rather special because this thing is going to be a multiple of the identity. We could call it the scalar part of the dihedron D. So it's actually the half trace of D times 1. While this thing here, we could call that the vector part of the dihedron. So now we have that the dihedron D consists of the scalar part of D, S of D, plus the vector part of D, V of D. And if we want to, we can sort of think of that as some multiple of the identity, because that's what this is, plus a vector. Okay? And this vector is in the transverse direction. So this is a kind of a geometrical picture for the dihedrons. It's a four-dimensional space. Here's the axis, the t-axis in the direction of the identity. And this thing here is supposed to represent a three-dimensional cross-section like we've seen. Okay? So that's like the vector part, and that's like the scalar part. So if you have a general dihedron D, it will decompose into a component in this scalar direction, multiple of the identity, say S of D times the identity, and there will be also a component in this vector part. So this is an algebraic way of seeing this geometrical decomposition in terms of these subspaces. One-dimensional subspace in this direction and this three-dimensional subspace in this transverse direction. Now, in terms of the conjugation, the T star is T, okay, and the V star equals minus V. So the component in this direction is unchanged under conjugation, while the component in this transverse direction is negated under the conjugation. Now, when we go to complex numbers, these are usually called the real and the imaginary parts. Okay, so it's sort of like that, but it's a little bit different, and it's more general, so it applies across the board to the entire dihedron algebra. But if you specialize to the complex numbers, then you can sort of pick up the subdivision into real and imaginary parts that maybe is more familiar. Okay, so the theme here is that a lot of things familiar with complex numbers are really restrictions of bigger things that are happening in the dihedron algebra that have an algebraic aspect and also a corresponding geometric aspect. All right, now we come to a very important algebraic aspect, which is the question of invertibility. We're trying to establish a numerical system here, a way of doing arithmetic, and when you're doing arithmetic, it's always division which is the most problematic. Here also. So the question of when an object is invertible is almost always a key question in arithmetic. And the answer here is given by this theorem that if D is a dihedron, then it's invertible precisely when its quadrants, Q of D, is not equal to 0. And in this case, the formula for the inverse is given by this. D inverse is equal to 1 over this quadrants times D star, the conjugate of D. So it follows from the fact that D times D star equals D star D equals the quadrants of D times 1. So if this quadrant is non-zero, then you can divide by it, and then you have an element that you can multiply D by to get the identity matrix. Right? And conversely, if this quadrant is 0, that means that D times D star is 0 matrix. That means that D is not going to be invertible. It's not going to be invertible because if it was invertible, then you could take that equation and multiply by the inverse and deduce that D star was equal to 0. Okay, so invertibility now is a question of whether this quadratic form is 0 or not. So you're used to, in ordinary complex numbers, the idea that you can almost always divide, but you have to make sure that the denominator is not 0. Now we're seeing that the bigger way of thinking about that, the more broader general way of thinking about that, is that you can divide as long as the thing that you're dividing by does not have quadrants 0. So it's not critical that the thing be 0 or not. The critical thing is whether the quadrants of that thing is 0 or not. So what do these quadrants look like? Well, in the blue familiar situation, the quadrants of a plus bi is a squared plus b squared. In the red geometry, the quadrants of a plus bj is a squared minus b squared. Well, you can see that that could be 0 very easily if a happens to equal b, or maybe a equals b bar, or negative b, then that's going to be 0 without this element being 0. So in the red geometry, and also in the green geometry, it's exactly the same kind of formula. The quadrants of a plus bk is a squared minus b squared. In these two geometries, we have to expect that there will be non-zero dihedrons which are not invertible because their quadrants is 0. And if the quadrants is 0, you can't divide by it. So if you take one of these complex number subalgebras, maybe the blue ones, the red ones, the green ones, when is this thing a field? A field requires that all the elements be invertible except for just the 0 element. So the answer is that CR and C of G are never going to be fields because, as we've seen, there's always going to be non-zero elements whose quadrants is 0, and if the quadrants is 0, then they're not invertible. However, in the blue geometry, it's more subtle. Okay? The answer is sometimes. Sometimes C sub blue is a field. It's going to be a field when the underlying field F that we're taking our numbers from has the property that a squared plus b squared equals 0 implies a equals b equals 0. Now that's happening in the rational numbers. So for the rational numbers, this property is satisfied. So the quadrants of a dihedron will be 0 precisely when the dihedron is 0. And it will also, in fact, work for a finite prime field. So finite field indexed by primes. P is a prime. So it turns out that if P is a prime which is congruent to 3 mod 4, like 7 or 11, or 19, but not like 5 or 13, then it's the case that this is true, that a squared plus b squared equals 0 implies a equals b equals 0. That means that over these kinds of fields, the blue complex numbers are themselves going to form a field. However, if P is congruent to 1 mod 4, which is the other possibility, then you're not going to get a field. So number theoretical considerations come into play here. But importantly, we do not want to dismiss the cases where we don't have a field. We do not want to be thinking about this as being contained in field theory. It's a very important thing to understand. Okay? We're not just thinking about field theory. We're talking about arithmetic, of creating arenas for doing arithmetic which are useful. And an arena for arithmetic can be useful without it being a field, as long as you're able to control division. And with these algebras, you can control division very clearly. Okay, so, and let me just point out again that in, say, the red complex numbers, 1 plus j, which is this complex number, is not invertible. Its determinant is 0. And in the green geometry, 1 plus k, which is this one here, is also not invertible. Its determinant is also a non-zero. So it's clear that these things here are not fields. But that doesn't mean that we should exclude them from our arithmetic. No, 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 no. Okay, these are still very, very important arenas for doing arithmetic because we can control the non-invertibility of things. We know exactly when things are not invertible because we have the quadratic form, which is the determinant. So the algebra of dihedrons is definitely not a field because there are lots of non-invertible elements. But the invertibility is carefully controlled. So we're going to call this thing something new. Okay? It's an arena that deserves its own kind of special name. And we're going to use the term quadratic inverse algebra, which I think captures pretty well what's going on here. The invertibility in this algebra is controlled by the quadratic form Q, which in this case is just the determinant. Okay, but it's a quadratic form. And when we take the subalgebras that we've been considering, the subalgebra C sub B, C sub R, C sub G, okay, these are two-dimensional commutative subalgebras, then we get very nice arenas for doing arithmetic, and they will also be examples of these quadratic inverse algebras. But we'll see later on that there are actually also other subalgebras that are very interesting in this dihedron story. So this is actually a broader picture, not just restricted to these three kinds of complex numbers. So we are led to think about something we might call QIA theory. QIA standing for quadratic inverse algebra. And this is joint work with Dr. Gennady Notowidigdo, and it's work that's in preparation. So rather shortly, hopefully, we'll be able to show you some very nice treatment of this algebraic theory. So mostly today I've been summarizing algebraic aspects, but I do want to emphasize that this is very much a geometrical theory as well as an algebraic one. And it's nice to emphasize that by putting together, beside each other, the Quaternion story and the Dihedron story. In both cases, we have four-dimensional algebras, Quaternions, T and V, a three-dimensional space, say spanned by I, J, K, and actually the same story over here. It's just that when you look at this three-dimensional space itself, in these two situations, they look quite different. So in here, if you look just at this three-dimensional cross section, you get a three-dimensional space where the unit sphere is actually a real sphere, a familiar two-dimensional sphere in three-dimensional space. While over here, if you look at this three-dimensional slice, well, it's a richer story. It's a relativistic story with an aspect having to do with a 2+1 relativistic quadratic form involving a null cone in red and some hyperboloids of 2 sheets and also hyperboloids of 1 sheet. Okay, so it's a very rich kind of story. And there's also I, J, and K appropriately positioned in here. Now, what are we doing when we're looking at these complex numbers? What we're doing is we're slicing these four-dimensional algebras with two-dimensional planes. And the two-dimensional planes are very special. They all contain the identity element because we want to have an identity element. So such a plane is determined by taking the identity elements and taking one element in this transverse three-dimensional space, call it W, and then thinking about this cross-section as being the span of 1 and W. So all the combinations of 1 and W forming a two-dimensional plane, which you can kind of think of as a slice sort of like this. A two-dimensional slice in this four-dimensional space. And so choosing this W in this three-dimensional space really amounts to choosing a point in this three-dimensional space. And then you're looking at the line through that point and sort of adding those multiples to the multiples of the identity to get your commutative subalgebra. And over here, it's very much the same story. We look at two-dimensional commutative subalgebras. They're formed by taking linear combinations of 1, that's 1, and a W. W is some point in this transverse three-dimensional space. So in the picture here, we have to take this three-dimensional space and we have to choose some W. And then we look at the line generated by that. And then the two-dimensional plane is multiples of this W and 1. And now you can see why the story is richer here, okay? Because geometrically, there is more sort of familiar symmetry here. This is a sphere at least over the rational numbers. It's an important proviso. Over the rational numbers, there's more symmetry here. The directions look at least like they're more or less all the same. But over here, there's a lot of different directions. The directions in the direction of this hyperboloid of one sheet acting very differently to the direction that you get by choosing a point in the hyperboloid of two sheets, or taking a point on the null cone, which is altogether a different story. Okay, so in both cases, we can explain sort of what's going on. We're talking about two-dimensional subspaces, but definitely in the dihedron story, things are richer, and that sort of explains why in this story we're getting these blue complex numbers together with the red and green complex numbers, all as different kinds of slices, depending whether you want to augment one with I, or maybe J, or maybe K. Okay, that's geometrical explanation of why the algebra of the
Okay, so let me try to wrap things up by
providing you with a brief kind of summary of maybe some things to remember. That complex numbers actually can be defined over any field, and the right way of doing that is via the algebra of dihedrons. So we're really going to 2x2 matrices. That's a key understanding because it explains immediately why complex numbers have an intimate connection with two-dimensional geometry. Okay, some people think it's kind of amazing. You have this I squared equals -1, and then suddenly these complex numbers seem to have an intimate connection with rotations and dilations in the plane. From this point of view, there's nothing surprising about that at all because the complex numbers are being built from the 2x2 matrices. So of course, an action on the two-dimensional space is part of the story right to begin with. Another point, the complex numbers have relativistic analogs. There's not just the usual complex numbers, people. It's not just I with I squared equals -1. There's also J with J squared equals 1 and K with K squared equals 1. And those are numerical systems which are relativistic analogs of the usual complex numbers, whose mathematical theory is every bit as rich as the usual complex number story. Now that's a very big claim, okay, that many researchers could try to investigate. That means I'm suggesting that there is a complex analysis. There's harmonic analysis that you can do. You can talk about differential equations. You can talk about groups and symmetries. So a lot of the very rich structure of complex analysis and complex geometry have analogs, I'm claiming, in the red and green stories. And these sort of are, not exactly virgin territory, but very unexplored, relatively speaking. So we really want to try to understand that there's this threefold symmetry, and right now things are very imbalanced. The relativistic importance of algebra and geometry has to be brought up to speed. Okay, it's been more than a century since Einstein and Minkowski, and pure mathematics needs to get on board that train a little bit. Algebraic properties are often specializations of dihedron relations. When you approach this from the dihedron point of view and think of complex numbers as being what you get when you drill down into the dihedrons, then a lot of things become much more obvious. A lot of algebraic properties are just easy manifestations of more fundamental properties happening at the 2x2 matrix level. You've got all of linear algebra to help you and to organize things. So it's a very powerful point of view. Complex numbers are always quias, quadratic inverse algebras, not always fields. So we have to let go of this preoccupation with fields as the only sort of reasonable environments for doing nice arithmetic. No, okay? So there's broader arenas, and this is a very nice alternative framework. Now there is a wider lesson here to be learned, which is that a really broad understanding of maths requires both algebra and geometry. They are complementary disciplines. They are both pillars of mathematics. They are the pillars of mathematics, with algebra being sort of an extension of the more elementary arithmetic. And we really want to understand situations with the algebraic and geometrical aspects both in our vision. Okay, so we don't want to just be algebraists. We don't want to just be geometers. We want to have a broader, encompassing point of view. Now, for this to happen, we really need to modernize our approach to geometry, because our current approach to geometry is actually rather prehistoric. It's based on classical Euclidean geometry, which is not really Euclidean geometry. It's based on angles and lengths, which actually Euclid was careful to avoid. So these are actually not found in Euclid's geometry, but nevertheless they are considered to be fundamentals of Euclidean geometry, and everything is framed in terms of them. Big mistake, okay? To really understand geometry and its links with algebra, you have to let go of the angles, the distances, the fake arithmetic of real numbers, which doesn't really work, okay? And you have to move towards a more algebraic understanding of things. I realize this is a big ask, okay? But it's really important for educators and researchers to start appreciating that there is a lot better options to what we're currently doing. And a good starting point, rational trigonometry and universal geometry. So these are now established fields with dozens of beautiful new theorems and understandings ranging across not just classical geometry, but also hyperbolic geometry, chromogeometry, and a lot of different connections with things, including algebraic calculus. And the reference, my 2005 book, Divine Proportions, Rational Trigonometry to Universal Geometry. So this is a starting point for this point of view that we can do geometry algebraically. And ultimately, when you want to go further in the theory of complex numbers, you really want to adopt a point of view like this, where you're looking for geometrical concepts which are algebraic, so they can fit inside our theory without having to sort of rely on fake arithmetic involving infinite processes that don't actually work. Okay, so we've covered a lot of territory. Thanks for listening and absorbing these things and maybe slowly moving towards understanding these things. In our next video in this series, we're going to look at another famous math problem, which is very closely related to this one. We're going to be looking at another slice of the dihedrons, okay? And this other slice of the dihedrons connects with the classical theory of infinitesimals. So we're going to be addressing the question of how do you actually set up a proper algebraic theory of infinitesimals. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.